Abhishek is a recipient of NDSEG and NSF fellowships. He has spent ample of time at Google Brain, and his works have appeared in major conferences. And I'm sure you would have noticed some of his works. If you have been going to machine learning, robotics conferences. With that, I will give it over to Abhishek and take it from there and tell us all the exciting work you have been up to.
Great. All right. Thanks for the introduction, Pulkit. So as Pulkit said, my name is Abhishek. I'm a PhD student at Berkeley. And today I'm going to tell you guys a little bit about how we might construct learning systems for dexterous manipulation. So to start off, I want to tell you a little bit about why I think we should care about dexterous manipulation. And so we have robots that have been deployed in scale in these industrial type settings, doing things like box packing or pick and place, but significantly fewer of them have been deployed into these unstructured human-centric environments. So things like the living room or a kitchen or a hospital, you have significantly fewer robots deployed into these types of environments. And I think that this is where there's a huge, tremendous potential for impact. And we need to build robotic systems that can actually deal with the diversity and variability of these types of environments. Right? So what does this have to do with dexterous manipulation? I think that in industrial settings, often you're performing the same task over and over again with minimal change in context. And so manipulators like vacuum suction cups or barrel jaw grippers can work pretty well. However, in these human-centric environments like a kitchen or a home, for instance, you have a wide variety of different tasks, often requiring fine-grained manipulation and dexterity. And in these types of settings, these manipulators might not work particularly well across all of the tasks that we care about. Now, an alternative here is to use these dexterous multi-fingered robotic hands, right? And the way that I think about it is that the world is made up of the world is designed for humans, and humans use multi-fingered hands. So why not use multi-fingered robotic hands to manipulate human-centric worlds? So if we think about how we might build a robotic system for these unstructured environments, I think it's a combination of choosing the appropriate robot and then choosing a scalable control algorithm, right? So you need to choose a robot, which as we discussed, might be something like a multi-fingered robotic hand. And then you need a way to control this robot in order to do useful things. So a scalable control algorithm that can actually perform goal-directed behavior. Right. Okay, so how do we actually do this? Well, one technique that has been used with great success is to leverage planning and trajectory optimization techniques with known powerful models, right? So what these techniques assume is some knowledge of an analytic model, and then leverage powerful planning or optimization techniques in order to actually get controllers. And this actually works pretty well, can scale to these types of dexterous manipulation tasks when the model is reasonably good, and it produces complex behaviors. But the challenge here is that if you go to these diverse variable worlds and you have a huge variability in the types of tasks that you're doing, often with complex contacts or dynamic motions, getting a great analytic model can be difficult. And in these types of scenarios, maybe relying on an analytic model can be too challenging for this to scale. And so I think that's what would bring us to using data-driven methods, right? And so an alternative to using analytic models is to say, can we acquire controllers from data via machine learning techniques, right? So the formula of combining large data sets with flexible function approximators has been used pretty successfully in language and vision with ImageNet, GPT-3, and there's n number of things that have been done. But this begs the question of whether a similar formula might also work for robotic control, right? So a paradigm that I find particularly appealing is that of reinforcement learning. And in reinforcement learning, you'd have an agent which is interacting with the world, collecting its own data, trying to maximize some notion of reward. Right? And when you combine this with a flexible function approximator, it has the potential to acquire pretty complex skills, which are pretty general purpose. So given that we have the data-driven reinforcement learning paradigm in our mind, how do we actually apply it to these types of real-world dexterous manipulation problems? So one option here is to use this paradigm of simulation to reality transfer, or sim to real, as people like to call it. And the paradigm involves training, reinforcement learning agent over a number of different simulations, and then saying that you're going to take the learned policy or the learned model and then transfer it to the real world, relying on the generalization of your model to transfer behaviors to the real world. And this is pretty nice because it requires minimal real world infrastructure. A lot of your training is done in simulation. And you can use lots of different privileges during training. So for instance, you can use arbitrary resets, or you can use rewards coming from wherever. You can use whatever simulations you want. You can set up a curriculum. So these are all nice things about these sim to real transfer methods. But I think that there's something that's fundamentally unscalable about these types of methods. And the way that I look at it is that there's a fundamental content creation problem. So for every new task that you go into, if you have to create a new simulator, which is reasonably accurate, this quickly becomes unscalable as you go to more and more environments, and especially the complex types of environments we care about here. Secondly, since we're relying on a data-driven method, the data needs to come from the right distribution. But in a multi-fingered robotic hand with a lot of complex dynamics, you're always going to have some amount of model misspecification, or you're always going to have some amount of domain shift, right? So if you keep collecting data in these slightly incorrect simulations, there's no guarantee that you're going to keep getting better. And if you're not going to keep getting better, then you're not really making the best use of these data-driven methods. And lastly, it's a more pedantic point, but if I have a grid simulator, using model-free reinforcement learning is not the best way to get a controller there. Right? There's lots of better ways that I can do that. But I think these challenges will make the sim to real transfer problem, even though it seems promising in the short term, maybe not scale as well to long-term deployment of robots in the real world. So an alternative that we can consider is doing reinforcement learning directly in the real world, right? And so what this involves is taking a robot, dropping it directly into the types of environments we want to deploy in, letting it collect its own data with some knowledge of what type of task it wants to solve, and then continuously improving as you collect more and more data. Now, the nice part about this is that you can explicitly avoid any explicit models being provided by a human. And since you're collecting data from the right type of distribution, which is the real world that you're trying to deploy in, you can guarantee some sort of continuous improvement as you collect data, with caveats, of course. But the nice part is that you don't have any domain shift. You can have continuous improvement. And this overall seems like it would scale as we can collect more and more data. And this is particularly well suited to the dexterous manipulation problem, because often it's harder to build a perfect model of a dexterous manipulation system than it is to just allow the dexterous manipulation system to interact with the world. Or at least that's what I'm going to argue for today. All right, so the key question that I'm trying to ask in today's talk is, how do we build dexterous manipulation systems that can use reinforcement learning to learn directly in the real world? Okay, so a natural question that comes up when we think about this research question is, why is it any different than any other type of reinforcement learning? Right? We've taken reinforcement learning, we've applied it to lots of different problems. We've applied it to AlphaGo and lots of simulated locomotion and Atari games, and the algorithm hasn't really changed that much. So what is really different about real-world RL for robotics than all of these other applications? And so I'm going to go into more detail about this through the rest of my talk. But I think what this boils down to is that if you do real-world RL, it has to abide by the conditions of the real world. You can't make up assumptions. You can't make up conditions, right? And so when you're trying to develop both algorithms and systems in order to perform real-world RL, you have to take into account the conditions and available assumptions under the real world, right? And the way we design our algorithms and systems right now is often not really taking that into account. So they make these unrealistic assumptions. For instance, if you have an algorithm in simulation, it might assume access to a really large number of samples, or arbitrary exploration, or teleporting resets, right? Or if you have a learning system that typically assumes access to something like rewards or resets during training, or access to low-level states. So in general, the algorithms and learning systems we design aren't really designed with the real-world reinforcement learning paradigm in mind. And I'm going to talk about how we can actually design better algorithms and better learning systems with this in mind today, specifically targeted towards dexterous manipulation. Okay, so that brings me to the general outline of the talk. I started by providing some motivation for the types of problems that I care about and why I think real-world reinforcement learning is a suitable choice to solve these types of problems. Next, we're going to talk about how we develop suitable learning algorithms to learn these kinds of behaviors in the real world. Next, we're going to be talking about how this is more than an algorithms problem, but it's actually a systems problem, and how do we design the right systems to perform reinforcement learning. Then I'm going to provide some perspectives on how this fits into the broader picture of robotic learning. Are there any questions so far? Okay, great. So let's start by talking about algorithms. Right? So the first question we want to ask is, what are the requirements that we actually have from these real-world reinforcement learning algorithms for dexterous manipulation? Well, we're using dexterous manipulators, so the first requirement is we actually need to be able to solve these high-dimensional problems with high-dimensional state and action spaces and complex exploration behaviors. And because we're operating in the real world, you're going to have noise and uncertainty, and so we need to acquire robust behaviors which are able to deal with this kind of noise. And lastly, if we want to learn in the real world, it has to be efficient enough for it to be practical. And so what we're going to try and ensure is that our training procedure is able to acquire these types of behaviors, but do so efficiently enough to be deployed. So the first thing that we can try and do to assess where we stand with respect to these requirements is to just try a standard reinforcement learning algorithm, right? So let's take a standard real-world reinforcement learning algorithm. Let's say we take an on-policy algorithm and we directly apply it to these problems of dexterous manipulation, right? So let's say we consider two different tasks, maybe picking up an object, opening a door, and we directly apply real-world reinforcement learning to these problems, or I guess it's not real-world, but directly apply vanilla reinforcement learning to see how feasible this is for the real world, right? And if we look at the resulting learning behaviors, we have in green the learning performance if we use a dense reward function, which is very carefully designed. And at the dotted lines at the bottom, we see the performance if we use uninformative sparse reward. And so the nice part is that if we have an informative enough reward function, we can actually learn the behaviors that we want. So we can solve these high dimensional search problems. But the challenge is that if you look on the x-axis, the number of hours that it's taking is on the order of 100 hours for something as simple as picking up an object. So this becomes completely impractical for us to deploy. So if we go back to our desired requirements from these algorithms, we see that you're able to solve high dimensional problems with high dimensional state and action spaces. But as we'll talk about next, the behaviors are not very robust, and they're definitely not efficient enough for them to be practical. Okay, so it's clear that we need something better. How do we actually get there? So while we can make a bunch of improvements on our algorithms, we can go model-based, we can go improve the stability of our algorithms and so on, and this can provide some amount of improvement. I think the biggest improvement can actually be obtained by changing the problem assumptions just a little bit. So the idea here is, what if we assume a little bit more supervision in the problem? How do we use a little bit more supervision to give us a lot of improvement, right? So we're going to assume we have a small amount of human-provided data, and we're going to take the small amount of human-provided data, use it to bootstrap a learning algorithm, and see if we can do a lot better. This data can be collected pretty easily with techniques such as teleoperation or even kinesthetic teaching. And the nice part here is that since it's still data-driven, it scales more favorably than something like an analytic model or a hand-defined controller. And so the key research question that I'm going to discuss in the algorithms part of this talk is, how do we take a small amount of human-provided data and incorporate it into the reinforcement learning process so that we can do significantly better than before? So let's say you had a human providing you some data. The question becomes, do you take this data, do you use it to influence the rewards, do you use it to directly influence the policy, something about the actions? How exactly do we affect the learning process? Okay, so to make this more concrete, let's first consider the scenario where the prior data is a small number of expert demonstrations from a human, right? And the question becomes, how do we take these expert demonstrations and bootstrap a reinforcement learning algorithm from them? And so when I hear the word expert demonstrations, the first thing that comes to mind is imitation learning. So imitation learning paradigms, especially via supervised learning, would take expert data and try to mimic them with some sort of function approximator which tries to produce the right action given the right observation. But imitation learning algorithms, while they're just designed to mimic behaviors, they don't really make for continuous improvement. But the nice thing here is that we can take some inspiration from these imitation learning algorithms and use them to bootstrap reinforcement learning algorithms more generally. All right, so this is exactly what we did in our first attempt towards this problem. And the insight here is that you're going to have demonstrations help guide your exploration throughout your learning process, while your reinforcement learning is going to allow you to learn complex tasks while continuously improving with data. And so this algorithm, which we call demonstration augmentation demonstration augmented policy gradient, or DAPG, consists of a couple of different steps. So you start by just initializing your policy via imitation learning, some sort of supervised learning procedure. And then you say, okay, how do we take this and improve further? Where we perform reinforcement learning with a slightly modified objective. And the modified objective looks something like this. It's a combination of a reinforcement learning objective and an imitation learning objective. And the reinforcement learning objective says, try to maximize the rewards as much as you can, whereas the imitation learning objective says, try to stay close to the expert actions on states encountered by the expert, right? And this objective, while it seems a bit ad hoc, actually makes a lot of sense. So if we think of reinforcement learning as the reverse scale divergence between, the learned policy pi and an expert policy pi star, and imitation learning is the forward scale divergence between pi star and pi, we can think of this objective as just a combination of the reverse and forward scale. Right? So the intuition here is that you're going to provide some initialization, but you're also going to make sure that the demonstrations provide you guidance throughout your learning process. Okay, so this algorithm is pretty simple. Let's see how well does it work on the types of dexterous manipulation problems we're considering. So we see that we can solve tasks like object pickup and relocation with a sparse reward function, which is just an indicator when you reach the goal. And you can solve this in the order of 7 to 8 hours. And the same applies for things that require more finger coordination, like in-hand repositioning of a pen, or picking up a hammer and hammering things in, which requires some amount of force, as well as multi-stage behaviors like opening a door. And all of these can be solved with just a simple indicator reward function, and then in pretty reasonable amounts of time, right? So if we look at the efficiency a little more closely, we can see here that if we compare with standard imitation learning algorithms or standard reinforcement learning algorithms, you start to experience reward a lot more quickly. So the green and blue lines shown here in the plot are DAPG, whereas all the other lines are standard reinforcement learning or standard imitation learning. And so we are able to continuously improve, and we're able to do so significantly quicker than if we didn't have these demonstrations. And I think what's really interesting here is if you actually look at these behaviors a little more closely, we see some interesting things. So if you look at these behaviors, we see that the behavior is actually really natural. So in tasks like picking up the object or hammering things in, if you just use reinforcement learning from scratch, you see a lot of this weird reward hacking. So it performs the task that you care about, but it does so in a kind of unnatural way. Whereas if you use demonstrations, it encourages significantly more natural behavior. And secondly, is that if you try and perturb the scene, so if you try and change the mass of the object, change the shape of the object, introduce general perturbations into the problem, you see significantly more robust behavior if you use a small amount of these demonstrations in the learning process. And so overall, this doesn't just give us efficiency benefits, it also improves the quality of the behaviors that you're able to learn. And so that's pretty nice.
Could you tell us how you generate the imitations for that? Is that, do you have some Dexterous teleop setup that works for this?
Yeah. We have, we used a cyber glove, and then we used a cyber glove to just control the hand in Mojoko where we're able to pick things up. So it's based on a system from Emo, Todorov, and Vikash at UW.
And is it natural even for hammering?
It is a little tougher for hammering. Yeah, it's a little tougher because the thing falls out of the hand more often. But I think if you get just the right angle and you press it just the right way, it works. So yeah, that's a good point. It's not perfectly natural.
But did you have the cyber glove with the force feedback, or just the passive cyber glove?
No force feedback. Yeah, just visual. Okay, so we showed a bunch of results in simulation. Does this actually work when you apply it to some real-world dexterous manipulation problems? So we see that pretty much the same algorithm, when you take it and apply it to dexterous manipulation with a 3-fingered robotic hand, does pretty useful things. So we have valve rotation here, which is just rotating a valve to different angles with this 3-fingered hand. And we see that we can learn this directly with the APG in the real world. And this also applies to tasks like in-hand rotation of an object, and even things like deformable object manipulation. So we have a foam screw here, which might be pretty hard to actually simulate, but it's able to learn in just a few hours of training in the real world. We can also scale this to do things with more complex behaviors, which involve an arm plus a hand moving and a deformable object handle. And what's nice here is you can actually take the same algorithm and throw it onto a totally different manipulator with no changes, and it seems to work pretty well. So here we have the Allegro hand, which is a 4-fingered hand, and exactly the same algorithm, reward function, and it seems to learn in roughly the same amount of time. So if we look at the quantitative results, you're able to learn around 3 to 4 hours of real-world training just by incorporating a small number of human demonstrations into the process. Okay.
So Abhishek, can you give a sense of how much is the reward if you only have the human demonstrations and you try to repeat them in the real world that you have?
Yeah, so I don't know if I have the curves here, but I think if you just do imitation learning, you get around 20 to 30% success rate. And if you like do reinforcement learning, you get up to 80 to 90% success rate.
So did you have to set up the environment in any specific way to ensure that, random exploration is happening correctly? Or so for example, if I move the object a little bit, would it also work in that setup? Because I guess demonstrations are collected from, one setup of where the object hand placement is.
I think we didn't really have to manicure that very much. What we did do is we did collect demonstrations from a variety of setups. So we didn't actually just do a single position. We did introduce some diversity into the demonstration. So there was some amount of generalization. And it works a lot worse if the demonstrations are really narrow.
Okay.
I have a question. For that picture there,
Yeah.
In order to generate the expert, the expert demonstrations, did you tell the humans to only use 3 fingers?
Oh, so for
that?
these particular pictures here, we actually did it with kinesthetic teaching. So we had me and 2 other people hold the fingers and move them around. So it was a bit of a contrived setup, but yeah. Okay. So the same idea of incorporating these demonstrations into RL can actually be scaled to more difficult to use manipulators like soft robotic hands. And so in this work, we showed that we can actually use a small number of human demonstrations to guide this soft robotic hand. It's, I believe, the RBO hand from TU Berlin. And we showed that we can use reinforcement learning with these demos to solve tasks like moving the beads of an abacus or rotating a valve. And this is much harder to control because it's just controlled by opening and closing a valve and releasing air into these chambers. And so while I don't have enough time to go deeper into the details of this particular setup, the point I want to convey is that this general idea seems very broadly applicable across even more difficult manipulators. Okay, so the question that naturally comes up here is, are we done yet? Is this algorithm satisfying all the criteria that we care about? Can we just directly apply this to the settings that we discussed at the start? So if we look at the criteria that we started off with, we see that we are able to solve high dimensional problems. We are able to acquire somewhat robust behaviors, and the learning is, it seems kind of practical, right? But this comes with caveats. So the first one is it actually practical? It's every new task that you have, and especially even if it's pretty restricted, is still taking on the order of 3 to 4 hours, which becomes pretty difficult to scale across many different tasks and many different variations within a task. And the second and perhaps more problematic part is that it requires this expert-only data. So you can't actually give it any of the failed demonstrations. You can't give it any suboptimal data. It needs the data to be great. And so this becomes pretty expensive for us to apply in a general purpose setting. And so it begs the question, can we develop more efficient reinforcement learning algorithms that can leverage a broader class of data? Right? And so this brings me to the second scenario, is how do we actually incorporate a broader class of data beyond just expert demonstrations? So, so let's look at some type of data that looks like this on the left, where it's not really expert demonstrations, but it's not complete failures always. It's partial successes. And can we incorporate this, arbitrary data into the reinforcement learning process? And to do so, I'd like to appeal to this paradigm of off-policy reinforcement learning. And what off-policy RL does is it says that you can utilize all of your past data rather than just your latest batch of data. And you do so by leveraging a combination of temporal difference learning type algorithms and explicit replay buffers that stole all your past data. And so these algorithms include things like Q-learning or DQN and actor-critic algorithms, and lots of work from the early 2000s and 90s as well. And so the way that I kind of summarize this general recipe is that it combines a policy evaluation step, which tries to get your Q function to evaluate how good your policy is, and a policy improvement step, which tries to choose the policy which maximizes the current Q function. And you alternate between policy evaluation and policy improvement. Okay. So given off-policy reinforcement learning in mind, how do we actually apply off-policy reinforcement learning to bootstrap from these type of human demonstrations or human data? So the idea is really simple. Because off-policy RL isn't assuming anything about your prior human data, you just take your human data and you throw it in the replay buffer. Right? You label it with some notion of reward, which tells you how good that data is, and then you throw it into the replay buffer, and then you perform off-policy reinforcement learning just as usual. And so once you throw it in the replay buffer, you can perform some amount of offline training where you train your actor and critic by sampling from your replay buffer. This provides you some reasonable initialization for your Q function and your policy, and then you can collect data online to continue to improve. And the nice part here is because you're making no assumptions about your prior data, you can utilize all of your past data. So not just your demonstrations or not just your latest batch of data, but all of the iterates that are in between. Secondly, because you're making minimal assumptions about the prior data, you can have expert data, you can have non-expert data, you can even have random data if you want. Right? And the resulting algorithm seems really simple. You just add the prior data to the replay buffer and continue training. Okay, so let's see, this seems reasonably sound. What happens if we actually apply this to those kinds of problems? If we look at some empirical results, the lines to focus on here, I'm a little colorblind, but I think it's the brown and the blue lines. And what we've done here is we've applied the same paradigm that I described last of bootstrapping from these prior data. And we've said, can we compare it with training from scratch? And so we see that while you start off pretty good, sometimes you have this huge dip in performance and then you continue improving, but the behavior is no better than as if you're learning directly from scratch. And this seems pretty odd. It seems like we haven't violated any assumptions. It seems like, off-policy reinforcement learning should be able to incorporate this data. Why isn't it any better than learning from scratch? And the reason behind this is kind of subtle. It can be attributed to this issue with distribution shift. And distribution shift is when your training and test distributions don't really match. And this happens internally in the process of bootstrapping from this off-policy data. And so to see where exactly this happens, let's consider the Bellman update, right? So in the Bellman update, you're going to try and make your Q function similar to a Q target, which is R plus the expected Q function at the next state with actions sampled from your current policy. And so if you look at this update and look at it a little more closely, you see that the Q function is evaluated at the next state on actions that are sampled from the actor, right? And because the actor is completely unconstrained, what can happen is that your Q function at the next state can be queried with an arbitrary action that it's never seen before. And if the Q function is queried with something that it's never seen before, something that's totally out of distribution, it can be arbitrarily over or underestimated. And if that happens, then your Q target is completely wrong, and that's going to make your whole Q function completely be off, and that's going to mess up your actor, and it's going to propagate and lead to lots of bad things. So to understand this a little more carefully, let's look at this graphic right here. Right? So let's say we have the data shown in the dotted line, and we have a fitted Q function in distribution shown by the solid blue line. So in distribution, everything looks great, but if you go out of distribution, as shown by the figure on the right, there's no guarantee that your Q function is going to be great when you query it on any out of distribution action. And so if you query it on something out of distribution, it can be overestimated, and that can be used for a backup, and that's going to propagate bad value. And this is particularly problematic when these Q values are overestimated, because they can continue to be backed up erroneously, making things that aren't actually good seem particularly good because of the distribution shift problem. Okay, so to understand this, let's consider like a little didactic example, right? So let's say we have a little MDP here. The green circles refer to things that are in distribution, and the red circle is something that's out of distribution. And let's say the red circle was the overestimated Q value, and you're doing Q learning to back this up. Because the red circle has been overestimated, it's going to be backed up into the middle node. Now the middle node is going to have the wrong Q value, and it's going to choose the wrong action for the next step. And this is going to continue propagating back in the chain. And though your overall Q function at all the states is going to get a little messed up. And so this is kind of what leads to the dip in performance, because you essentially start back at starting from scratch. And this is particularly problematic in the offline training phase of things, because what happens when you're offline training is that you can't actually collect more data to correct for this over optimism problem that you have, right? So you're kind of stuck backing up incorrect values over and over. Okay, so how do we actually fix something like this? Right? So a simple idea is, okay, if out of distribution actions are the problem, just don't take out of distribution action. Right? So if we take the actor critic update and we say, in the actor update, you performed a constraint optimization instead of just the standard actor update, and you say, stay close to the data that you've seen so far. Right? So minimize the divergence between pi and the behavior policy, which represents all the prior data. Why would this actually do anything sensible? Well, if you go back to the graphic that you had earlier, you're going to get a huge penalty anytime you try to choose an action that is out of distribution. Are you going to get a penalty, or the Lagrangian is going to blow up, or depending on how exactly you enforce the constraint, it's going to be unhappy. Right? And so depending on the choice of constraint that you have and the choice of enforcing the constraint, whether you want to do it via dual gradient descent or penalty method, barrier method, whatever, it leads to different types of algorithms. Right? So you have algorithms like BEAR, bootstrap error accumulation reduction, batch constraint queue, BRAC from people at Google, and all of these have the same idea. You're going to have constraint optimization on the actor, and that's going to prevent out of distribution bootstrapping. Okay, so this seems like great solution of the problem. Does it actually work in the scenario we care about? So if we go back to some empirical results, we see that these types of methods are actually overly conservative. So let's take a great performing method for offline RL like BEAR, and we directly apply it to this bootstrapping with online improvement sort of paradigm. And we see that even though it starts off pretty good, the line in yellow starts off pretty reasonable, it doesn't actually improve with more data. And now if you loosen the constraint, it does continue to improve, but then there's the huge dip in performance. So we have a bit of a catch-22. It's like if we have the constraint enforced, we're not improving. And if we loosen the constraint, then we lose all the benefit of offline training. Right? So why exactly does this happen? It seems like this shouldn't be happening because you're collecting data online. But what seems to be happening is that when you enforce this divergence between your current policy and the data distribution that you've seen so far, you have to do so by enforcing this divergence between pi and some pi beta, which is the distribution of actions that were seen in the prior data. And to actually do this, we have to fit a density model for pi beta. And doing this would do some sort of maximum likelihood estimation. And this often becomes difficult when you're doing online training. So to kind of see this a little more clearly, let's plot the log likelihood of offline and online data under a fitted behavior model. So we see that offline training, everything is high likelihood you're doing well, but as you continue doing online training past the middle point, the offline data has significantly higher likelihood than the online data. And what that means is that your behavior model is putting much higher likelihood on everything you've seen in the past than the new data that's coming in. And if you do that, then the constraint is never going to let you incorporate the new data in, and it's going to be overly conservative, keeping you back to the prior data that you had. Right? So it seems like there's an issue where we actually need to enforce a constraint to prevent out of distribution bootstrapping, but enforcing the constraint requires this behavior modeling, which becomes challenging with online improvement. And so that kind of brings me to the algorithm that we proposed here, which yes.
Just to be clear, over here, when you mean online data, you don't mean new data, you just mean changes in the policy, right?
No, I mean online, I mean new data. So I mean, like you train some amount offline and then you continue to improve online. So you're collecting more data online, right? And so that new data that you collect online to continue improving from the start is where the problem lies.
I see. So we are no longer in the setup you were introduced earlier where there was no new online data. Now you're considering what happens as you're getting online data with the conservative.
So I think, yeah, so I guess maybe I should have made that more clear, but if you go back to the setting here, the way that it works is that you do some amount of offline training and then you continue doing online training with data collection. So the offline training part I refer to as the pre-training, and then you do online training with more data collection after that.
And are you still considering optimal demonstrations over here, or
no, it can be arbitrary.
Okay.
Yeah. Okay. So to kind of avoid these issues of auto distribution bootstrapping and behavior modeling, what we can try and do is do implicit enforcing of the constraints. And this allows us to avoid this whole behavior modeling challenge. So the idea here is let's take the same type of update. You want to maximize the expected advantage or the Q function under the constraint between your policy and the past data. But instead of enforcing it via penalty or via dual gradient descent, what we're going to do is we're going to solve the KKT conditions. Right? We're going to get the optimal solution and then project it onto the parametric model via supervised learning. And so this is kind of the idea behind a lot of algorithms like RWR or REPS. And the idea here is that you're going to do a weighted supervised learning update. So if you look at the resulting update that you get if you crunch through the math, it looks something like this. And the way that I understand it is really simple. It says that you're going to sample states and actions from your prior data, beta, right? And then you're going to do a weighted supervised learning update where the weight is determined by the advantage of the current state action pair. So if something has high advantage, it's good. You're going to do supervised learning with a high weight, and low advantage, you're going to do supervised learning with a low weight. And the nice part here is because you're just sampling from the behavior policy, you don't actually have to do any density modeling for the behavior model, but you're still enforcing the same constraint because you're never querying the Q function on anything that's out of distribution. You're always sampling from the data that you've seen so far. So you're kind of avoiding the distribution shift while avoiding the difficult density modeling problem as well. So to make this a little more concrete, let's kind of lay out what the whole paradigm looks like, right? So the paradigm for a wake or a WAC is that you add some amount of prior data to the replay buffer, right? And then you perform actor-critic updates offline via supervised learning updates for the actor and Q-learning updates for the critic. Right? And then once you've done some amount of this pre-training, then you can do online training with actual data collected by the actor and then repeat the whole process using the same update. Right. So what this allows us to do is during the offline training, not have performance deterioration while continue to improve online. And if we go back to our graphics from earlier, we see that the reason that this works is that you're never actually going to query actions that are out of distribution, but you're just going to sample from things that are in distribution. Right? And so it allows you to reweight things that are in distribution without ever having to worry about the counterfactual queries. Okay, so this idea seems pretty easy. Does it actually work? It seems to actually work pretty well. So we applied it to the same types of problems, but we gave it less optimal data. So we gave it a mix of some optimal data and some suboptimal data. And we see that within 300K steps, which is around 45 minutes of sample time, we're able to get around 90% success rate, while off-policy RL, standard offline RL methods, and our prior algorithm of DAPG still stays stuck. Right? So DAPG will eventually get there. It just gets there a lot slower. And the same is reflected in the learning curves as well, where we see that across different tasks, we're able to learn significantly more quickly and get a lot of benefit of the offline pre-training using an off-policy RL algorithm. Okay, so this seems pretty good. In fact, we can actually take this insight a bit further and notice that supervised learning is the common thread that made both of these algorithms work. Right? And in fact, you can take this idea of supervised learning further and use it with even less structured data. So you can learn from undirected random data playing with elements of the scene, or even starting completely from scratch to build algorithms that are able to solve tasks like this. I won't have time to go into the details of these algorithms, but the point that I wanted to make is that supervised learning is not just useful for offline training. I think it's also useful as a subroutine in reinforcement learning algorithms. Okay, so some takeaways that I have with the algorithms portion of this talk is that to build efficient, robust, and practical algorithms, we might want to use a little bit of extra supervision. And we can incorporate these things via either using on-policy algorithms or off-policy algorithms with tricks from supervised learning. And we can even generalize this beyond these types of data to less and less structured data sources. Okay, any questions? Okay. So, we've talked about how to develop, some suitable learning algorithms for learning these dexterous manipulation behaviors. And so the natural question becomes, okay, algorithms look great. Do we just take them and throw them at the real world? Will they just work in the types of environments that we care about? But if we look at this question a little more carefully, it actually requires more thought. And this is because learning algorithms don't operate in isolation in the real world. They actually operate in the context of an entire learning system. So if you have a great learning algorithm, it has the fanciest math, but it just doesn't get the right data, it's not going to learn anything, right? So this question needs to be considered in the context of the entire learning infrastructure. And what I'm going to argue for today is that we actually need fundamental improvements in the learning systems and infrastructure in order to do these kinds of dexterous manipulation tasks in the real world. Okay, so given that our discussion so far has revolved around data-driven reinforcement learning algorithms, what's important to remember is that the important part of data-driven algorithms is the data, right? And so if you have a reinforcement learning algorithm which is deployed to directly learn in environments like the home, the kitchen, hospitals, things like that, the question becomes, can we actually get these algorithms enough of the right type of data to learn the tasks they want to and continuously improve the data collection? So we know that we can do this in things like Atari games, simulated robotics, AlphaGo, but the question is, can we do this in these unstructured, arbitrary environments that we're trying to learn in? To answer this question, let's take a little bit of a closer look at some current real-world reinforcement learning methods, right? So we have some work from Google, some work from us, and some work from Anusha at Berkeley. And we see that we're able to learn some pretty interesting behaviors, and we're able to learn this by directly training in the real world. And so this is nice because it suggests that real-world RL can acquire behaviors. But if you take a closer look, this tells an incomplete picture, right? So all of those are showing the trained methods, but if you look at the actual training setups, they're highly instrumented and require a lot of human intervention. So the first setup actually requires a human which is going around and opening and closing all the doors and sensors on all the doors which tell you whether it's open or not. In our setup for dexterous manipulation, we needed this servo motor with a spool which closes the door after every trial so that you can try over and over, and sensors on all of the objects in the scene. And for Anusha's setup, she had to set up this funnel with a different robot which picks up the balls, puts it back into the hand so you can reattempt, and she had to script all of that motion. Right? So this is pretty far from this promise of like plug and play robotics where we drop an agent into an environment and it continues to improve. Instead, we have careful instrumentation needed for things like resets, things like state estimation, and even for providing reward functions. Right? And so the research question that I want to ask in the second part of the talk is, how do we actually build systems that allow these robots to collect their own data autonomously without needing any instrumentation or intervention from a human? Right? So why do I care so much about instrumentation or intervention? The reason, I think, is because an autonomous data collection system only scales as well as its weakest part. Right? So if you need instrumentation, it doesn't really work if you need to put it in an arbitrary environment because you have to instrument, you have to build this whole contraption. At that point, why not just perform the task yourself? And if you need intervention, this becomes problematic because it makes the cost of data significantly more. So if you have to hire someone to be with your robots all day and all night and just reset doors, it makes the whole process significantly more expensive. And this limits the amount of data that you can actually collect. So I think what we need is to build systems that can be left alone to learn with minimal amounts of babysitting. So what I'd like is I drop my robot in an environment, tell it what to do, and then it just keeps learning on its own without me having to be there all the time or me having to build a fancy contraption to let it learn. Okay, so the question becomes, why is this non-trivial, right? Why do we need all of these instrumentations or interventions? And I think this can be boiled down to a mismatch in assumptions between the idealizations of reinforcement learning and the real world. Right? For instance, RL idealizations assume access to episodic reset, which reset the scene after every episode. Something which tells you what low dimensional state you're in. So all the joint positions, all the object positions, things like that. And lastly, some reinforcement learning algorithms basically assume that reward magically shows up in the environment, but rewards don't magically show up in the environment. Right? So in the real world, we actually have no reset mechanisms. You just have a continual stream of experience that your robot is receiving. You usually don't have low dimensional state estimates. You have just camera images or sensors from your robot. And the reward function is not magically provided by the environment. You need to infer this reward function since rewards are pretty much imaginary. And so in order to build a real-world reinforcement learning system, I think we need to basically figure out the ingredients to tackle challenges like this. Right? So the ingredients of a real-world reinforcement learning system might include a component which is able to deal with the lack of a reset mechanism by doing reset pre-reinforcement learning. Something that's able to learn directly from high-dimensional sensor observations. And something that's able to do scalable autonomous reward inference. Right? And so while these can be instantiated in a number of different ways, let's try describing a simple one for dexterous manipulation today. And so what I'm going to be talking about first is what we call R3L, which is a system instantiation to perform dexterous manipulation. And the idea here is that you can deal with the lack of a reset mechanism via something we call a perturbation controller. You can learn from high-dimensional image observations by techniques for unsupervised representation learning. And lastly, you can deal with the lack of a reward function by using visual success classifiers and goal images. So, all of these words don't mean anything without more context. So let's go a little bit deeper into each of these and see how exactly we might build such a system. The first component we need to consider is how do we learn directly from onboard high-dimensional image observations, right? So while there are a number of reasons that can make learning from high-dimensional observations difficult, what we're going to focus on today is actually the dimensionality of these observations, right? And so you can use techniques like unsupervised representation learning to bring down the dimensionality of these observations and map from a high-dimensional camera image to a lower dimensional manifold. And this can then be exposed to reinforcement learning. So, reinforcement learning with deep function approximators doesn't actually need this. In principle, you should be able to learn from pixels to torques. But what we find is when learning from high dimensional observations is combined with the other challenges, the challenges of scalable reward inference and reset-free learning, this unsupervised representation learning component becomes really important. And so the way we did it is nothing special. We just used a standard variational autoencoder because it's simple and scalable. But a number of different techniques could be used. So contrastive learning, key point learning, predictive modeling, any of these things can yield representations that would be suitable. But the point that I want to make clear is that representation learning is useful when combined with the other challenges of reward inference and reset-free learning. Okay, so now that we're able to learn from high-dimensional observations, the next question becomes, how do we infer rewards autonomously for reinforcement learning? And as I mentioned earlier, the rewards don't actually exist in the environment, and you have to infer them. Right? So let's say we have a paradigm where a human wants the robot to make coffee. And if the human wants the robot to make coffee, they're going to try and communicate that intent to the robot, which is autonomously interacting with the world. The robot needs to take this communicated intent, needs to take the state of the world, and then infer some sort of reward function that it can actually use for optimization. Right? So the inference of the reward function is internal to the robot, and it's not being provided by the human. The human is just specifying what problem to solve. And if we use this kind of paradigm, the important things that we need to consider is how do we scalably communicate tasks or objectives to the robot, and how do we infer reward functions in a pretty scalable way that allows you to keep collecting data. And so what we did for this is to leverage this paradigm of providing successful outcomes. So we can say a human or a demonstrator comes in and shows you how successful outcomes looks with just single examples. And then given these examples, you can try and infer a reward function for doing learning. Right? So given these examples, the question becomes, how do we actually infer reward functions for continual learning? And the way we do it is extremely simple. We say these successful outcomes are treated as positive examples, and everything else that you collect on policy is treated as negatives. And then we just train a simple success classifier, which classifies the likelihood that something is the goal or not. And then we use the rewards from this classifier, or we use the likelihood of this classifier as the reward for learning. And then the nice part about this is that all you need to do is provide these goal images or these success outcomes at the start. You just need to leave the robot to learn, and then it infers its own rewards during learning. And this adaptively changes as you collect more and more data. Okay, so again, I'm going to stress this is not the only way to do this. This is just one instantiation that could work in a scalable fashion. And lastly, there's a problem that I think a lot about, which is learning without resets. And reset-free learning is not talked about very often, but if anyone's done a reinforcement learning experiment with a real robot, you know that you have to sit with the robot for days and days and days and just keep putting the object back in the hand of the robot, or keep resetting the scene to keep trying things. And the problem here is that this becomes quickly unscalable because it requires so many man hours to actually supervise the training. So reset-free reinforcement learning is difficult for a number of different reasons. The first reason is that when you're doing reset-free RL, the agent can get stuck. So let's say you're trying to push this cup somewhere, and you accidentally miss the cup, it goes out of the gripper. Now the agent will get stuck without the gripper around the cup for a long period of time. When you had episodic resets, you would just reset the object, reset the arm, and try again. But when you don't, you have to get yourself unstuck. Right? And the second problem, which is somewhat more subtle, is that when the agent actually successfully solves the task, it may actually stay at the goal. So once you solve the task, you get the cup to the location. The right thing to do is to not actually perturb anymore. And when you do that, the agent kind of stops learning. So you stop collecting meaningful data because you've just said you're at the goal, you stay there. And you've only experienced a pretty narrow set of outcomes that got you there. So you don't actually learn any sort of robust behavior. And this is evident empirically as well. So if you look at the training curve for this kind of task, it looks pretty good as shown in the dark green. But if you look at the lighter line, the learned policy is actually not very useful because its set of experience is extremely narrow. Right? And so what we need is a method that helps you get unstuck and lets you keep practicing the problem without stagnating the learning process. And to deal with this, we proposed a really simple solution, which we call a perturbation controller. And the idea here is that you're going to alternate between a regular controller and something that perturbs the scene. So you're going to have two controllers, a forward controller that's trying to solve your task, and a perturbation controller that's trying to perturb your scene. And the perturbation controller is just trained with an exploration objective. So it's saying, try to get yourself to as many new and novel states as possible. And then the forward controller will take you back to the goal. Right? And what this does, it helps you set up essentially infinite numbers of practice problems while also helping you get unstuck from these challenging states. And so the paradigm that we would use is to replace the reset phase of any standard reinforcement learning algorithm with just a run of your perturbation controller. So you run your policy, then your perturbation, then your policy, then your perturbation, and you continuously set up training problems for you to keep practicing. Okay, so the overall training system now looks like this. You have user-provided goal images. You provide these to the learning system, and you leave it to train for many, many hours. It learns from raw image observations with its own self-inferred rewards and without any manual resets provided. And lastly, you come back and it does useful things. So when we actually apply this to real-world problems, this is what we get. Right? So we start by showing it what successful outcomes look like. Then we actually just left it for many, many hours to train. And then it keeps practicing by setting up different positions of the abacus where it's trying to get to a particular configuration, and the valve where it's trying to rotate it to some particular angle. And then when you come back, you have a policy that's successful from a robust set of conditions. And this is interesting because it set up its own practice problems to practice from a variety of different positions. Right, so the general design principles here are that we need to make data collection as unsupervised as possible. And we're going to do so by having things that can autonomously infer reports and set up their own practice problems during training. Okay, any questions?
So this perturbation controller, was it trained to visit new states in the representation space, or was there some other,
Yeah, in the representation space.
Okay.
Just with a simple novelty based, like we used R&D, but like you could use any novelty based method.
Okay.
Okay, so we discussed, a reasonable system to do things, but the tasks that I showed are pretty simple. They're not very complicated tasks. So why is that? Why is it limited to these simple tasks? The reason is that exploration can often be pretty challenging, especially for reset-free learning. So let's say you were doing something with in-hand manipulation, right? And you dropped the object. Now you're stuck in this low connectivity state where you have to go and pick up the object and resume training. And this becomes really hard for an exploration algorithm to deal with. And so reset-free learning can be quite challenging in single task settings. But the next question we asked is, can this be much easier when you're actually learning multiple tasks together? So you're learning multiple tasks together. Can the tasks help each other somehow in the reset-free paradigm? And the key idea that we considered next was that when we're learning multiple different tasks together, some tasks can be used to reset other tasks. Right? So let's say you're doing many different tasks together. If you sequence them appropriately, then different tasks can help reset other tasks. And therefore, all of the tasks can be learned more effectively. Okay, so let's ground this in some concrete setups. Let's say we have an in-hand manipulation task, and we have a number of other tasks that are being learned, like recentering an object on the table, reorienting the position, picking up the object, and they're all being learned jointly. Right? And let's say you're trying to learn all of these jointly. One thing that's evident is that let's say you're trying in-hand manipulation and you drop the object, you can then recenter the object, reorient it, pick it up, and then resume training again. Or for pickup, if you fail at pickup, you can recenter, reorient the object, and try the whole thing over again. Right? And so when you're learning multiple tasks, if you have an appropriate way to sequence things, then you can actually learn all of them better. And that's kind of, some of the empirical results we showed here, which is that if you look at the training procedure, it looks something like this. You can see that there's no magical resets. The hand is just performing different tasks one after the other, trying to reset the scene and practice over and over. And so this is nice because you can now scale to significantly more challenging tasks just by giving the robot a huge diversity of tasks to solve. Okay, so the kind of takeaways that I want to cover here is that, well, most importantly, the important part of a data-driven system is the data. And if we want to scale data-driven RL to solve these kinds of difficult tasks like dexterous manipulation, we need to carefully consider the ways that we're collecting data in the real world. And this can be made challenging by a bunch of different factors. Most importantly, I think, are reward inference and reset-free learning. And if we think carefully about these things, we can actually design systems that can scale to real-world uninstrumented type scenarios. Okay. Lastly, let me kind of put this in perspective and where I think all of this kind of matters. Are we out of time, Pulkit?
We have a couple of minutes.
Okay, cool.
I think,
I'll keep it very short. Let's skip the takeaways here. I just want to tell you a little bit about what opportunities I think this affords going forward. So I think that because now we want to deploy robots into real world environments, we have access to real world data. And I think real world data offers a number of different opportunities. So the same way that, computer vision made a big jump when you had powerful optimization algorithms like SGD or ADAM and big real world data sets, I think reinforcement learning might also succeed if you move from an optimization problem to a generalization one. So RL is typically considered, if you're trying to manipulate a pencil, you just evaluate how well can you maximize the reward on that pencil. But this is weird because the training and testing are exactly the same with some caveats. But really what you want to move to is something where you have a train distribution and a test distribution, and you can study RL just like you study any other machine learning technique in terms of its generalization. So that's one thing I think is particularly promising. And secondly, I think a nice part about deploying robots into human-centric environments is the humans, right? And so while putting humans into the loop of artificial setups is, contrived, in real-world environments, humans are just there. And so we should be able to naturally leverage the human supervision and presence in these types of environments and build better interactive learning systems that are able to, learn from body language, learn from language, learn from gesture, leverage humans to bootstrap their learning process, so on. With that, yeah, I think those are two promising directions. I'd like to thank a huge number of collaborators. Yeah, thank you.
Yeah. Thanks, Abhishek.
Thank you. Yeah.
I think we have a couple of minutes for any questions.
Sure. Yeah.
I'll ask one if it's okay. That was a great talk. I really enjoyed that. Thanks for that. So lots of questions actually, but I'll pick one. So you talked about using human supervisory data in the beginning.
Yeah.
You talked later about possibly doing more complex perception using latent spaces for your policy.
Yeah.
Have you put those two together yet? And have you thought about how, presumably in the demonstration case, you sort of were able to infer the state of the system during the demonstrations.
Yeah.
Presumably you could, in the demonstrations, infer the latent state and use that to do some sort of, distributional constraint on the policy.
Yeah.
But is it clear that is that a different goal for the latent state than the standard autoencoder would do? Is there something?
Yeah, if I'm understanding correctly, I think what you're asking about is whether the latent representation needs to be somehow task directed or objective directed because they're being collected with demonstrations rather than just randomly unsupervised, right?
That's one aspect of it, but it could, in general, those two are not necessarily compatible. Like the idea of trying to stay near your data in latent space and just training your latent space. That might affect the way you'd want to train a latent space, I guess. I'm just curious.
Yeah. I think we haven't done that yet, but I think that task-directed latent space learning is much more effective than unsupervised representation learning. And so any algorithm where we do have access to that data, which I did argue for providing that data before, should make use of that. And so I think methods that are able to leverage like for instance, I think predictive models that would predict reward and next state would also be task directed in a similar way. And that might be, a pretty reasonable thing to do as well. So yeah, I think that would be good to look at next. Yeah. Thanks.
Can I ask a quick question?
Absolutely, yes.
Thank you, by the way, that was a great talk. In the multitask setup for you said free learning?
Yeah.
Do you have to categorize the state to decide which of the policies is going to get the data?
Yeah, so right now, this is really preliminary work. I think we just submitted it to ICRA. So right now what we do is we assume like a finite state machine with an oracle which tells you which task to deploy, which is essentially a classifier which tells you, which task is suitable.
Because in general, that can be a big problem.
Can be a big, that can be a big problem.
Okay, thanks.
Yeah.
So let's thank Abhishek once more for the talk.
Thank you.
If you have more questions, feel free to reach out to him, and maybe you can set up a one-on-one with Abhishek.
Yeah, I'm happy to chat. Shoot me an email or
Cool.
Thanks.
Yeah. Thanks, Abhishek. Thanks, everyone.
Thanks.